Okay, lots of notes today. So we're going back to rational functions. And if you remember in Unit 7 when we did the parent function, our rational function is the parent function 1 over x. So what we know is that we're going to have a horizontal asymptote and we're going to have a vertical asymptote. And in the parent function, that just happens at 0, 0. Okay, and so what we said is we can never ever cross the asymptote. We can get super close to it from both directions, but we can never cross it. So it doesn't matter which quadrant I have, I'm just going to get super close. I'm never going to cross it. Now, that's not entirely true. And so I'm going to step back on where we were. So what we know is we can't cross the asymptote in certain positions, but sometimes we can cross the asymptote in the center of the graph, but not out at our end behavior. And that gets really confusing. So what we're going to do is we're going to work through this, and you'll see it cross a lot in calculus, but in this class, we're going to walk through just identifying when it's continuous and when it's not continuous, and then graphing the function. Okay, so for what values of x is the function below not continuous? So remember, if it's not continuous, then I have to pick up my pencil and move it. So what this means is I'm going to have an asymptote, I'm going to have a hole, I can't have a hole, or I'm going to have a jump. All right, so let's look at this. I'm always going to go from left to right, just like we've been doing all year. So if I start over here at the left side of my graph, I'm going to start over here, and I keep going, and then all of a sudden, boom, I hit a hole. This hole is discontinuous, and that happens at x equals -2. All right, now I keep going, and now I have an asymptote. So I'm going to get super, super close to the asymptote, but I can't ever cross it, right? So that's going to happen at x equals 1. All right, so then I'm going to go back up and pick up my graph here. This is x equals 1 still, and I'm going to keep going, and then I have a closed circle. So now I have to jump down here to get to this point. That's why we call this a jump discontinuity. And so what happens is I'm going to jump or step down here, and then I can keep going again. So at 1, 2, 3, it is also discontinuous. Now, remember, a continuous function is something that's going to look like this, and I could just keep going and never have to lift up my pencil. So discontinuities occur when the function is undefined. Now, the function is undefined if there's not a value. There's not a value here. There's not a value at my asymptote. There is a value here, right? I can get a value because this is a closed-in circle, all right? But what happens is it's also undefined when the denominator equals 0. That's going to be really important as we talk about rational functions. So the two things that we're going to talk about here are going to be asymptotes and holes. Now, here's why. So what we just said is this has a hole. I do not have a value. So this is going to be a discontinuity. It's undefined. No value. This, my asymptote, I also have no value. It's undefined. But, like I just mentioned, on this one, I have a jump discontinuity, so this is discontinuous, but I do have a value. The value is my closed-in circle, which is, I don't know, 1/2. So it is not undefined. So because of that, when we're dealing with rational functions, we really only care about what happens at holes and asymptotes. If I have a jump discontinuity, it's okay because I can still have a value as long as one of them is equal. All right, so holes in my graph are going to occur. So holes occur when the graph factors cancel out. So remember, this is a rational function. I'm going to have a numerator and I'm going to have a denominator. So here's a rational function, which is much more complicated than what we have in Chapter 7. In Chapter 7, we might have something like this, right? So we said we have an asymptote at -2, we have an asymptote at -3, and then we graph it. Well, now it's a much more complicated. So first thing I have to do is I have to factor. So trial and error on the top, I'm going to get x plus 3, x minus 1. This gives me a negative 3 and a positive 2. And then I have x minus 1 in the denominator. Okay, so here's what happens. This factor of x minus 1 and this factor of x minus 1 are both going to cancel out. So what I'm left with is x plus 3. This is what I'm left with. So my new function becomes y equals x plus 3. Now, I could have gone in here and done synthetic division and said, I want to see if this is a factor, and I could factor it out, but it's not going to tell me if anything cancels in the top. So you want to just factor the top and get everything to cancel. Okay, so what factor canceled when we were simplifying? The factor of x minus 1. So now what we're going to do is we're going to graph this, and we're going to see what happens with this hole. So this is where the hole comes from in our graph. So we're going to set the canceled factor equal to 0. So I have x minus 1 equals 0. So I have this value of x equals 1. Okay, so now I'm going to go back to my very original equation, and I'm going to plug in 1. Okay, let me do that down here. So I have 1 squared plus 2 times 1 minus 3. That's my numerator. My denominator is 1 minus 1. So my denominator, I have 1 plus 2, which is 3, minus 3. So I end up with 0 over 0. This is what matters. I have a 0 in the denominator. This is not good, so this is undefined. So I have a hole, and that hole happens because if I take this factor of 1, which is what I get this factor of 1, it gives me a 0 in the denominator. So what's important about all of this? You need to factor it, you need to cancel it, and then you need to see if that cancels, then it's a hole. So I'm going to go back to my modified equation, right? So it says rewrite in factored form and simplify. So I did, here's my new equation. Now I'm going to take this value of 1 and I'm going to plug it in here. So y equals 1 plus 3, which is 4. So what happens is now I know the value. This is the value of my hole. So I can go over here and I can go to 1, 4, 1, 2, 3, 4, and I know I'm going to have a hole that's right there at 1, 4. If I was to graph this equation, this is a line now, mx plus b. I'm not graphing it as a rational equation. I'm graphing it like this. So I start at 3, I go up 1 over 1, and then I go down 1 over 1. So this is what my graph looks like. And I have a hole in the middle of my line now. So I'm going to pull out the calculator, and I'm going to look at this. And what I want to do is I'm going to put my original equation in my calculator. So remember, to get a fraction, you'll do alpha x or second y, depending on which calculator you have. And I'm going to say x squared plus 2x minus 3. And in my denominator, I have x minus 1. Now, when I graph this, I'm going to see a line. Now, here's where it gets tricky. I have a line, but I don't see the hole on my calculator. It's not there. So let me show you why this exists. So let's say I want to find the value of something on this graph. So what I'm going to do is I'm going to go to second trace, which gives me calc, and you don't have to worry about this. I just want to show you this. And I want to know what happens when x equals negative 1. So I can go over here to my graph. When x equals negative 1, I get the answer 2. Negative 1, I go up 2, I get this whole, or this point that's right here. So when x equals negative 1, this tells me y equals 2. Well, we see that on the graph. It works, okay? But now watch what happens. When I do second trace and I want to find the value at 1, remember, value at 1 is where my hole is. So when x equals 1, look what happens. There's no y value. So even though your calculator doesn't show the hole right here at 1, 4, the calculator knows that that hole exists. So there's no way for you to go to every single point and see where your holes are. You have to do it algebraically because the calculator is not going to show you where that is. Okay, just as another example, if I went in here and wanted to know what's the value at 1, 2, 3, negative 3, I should get a y value of 0. So let's do that. So at negative 3, it tells me my y value is 0. So the y value is going to show up if it's 0. If the y value doesn't exist, then it's going to be empty. All right, so that's a good way for you to go back and check your holes. Okay, keep going here. Our vertical asymptotes occur when the denominator, denominator doesn't cancel. All right, so we have another function here, and for us to know if it's going to cancel or not, we have to set this equal, we have to factor this. All right, so numerator doesn't factor. Down here, I'm going to do this by trial and error. So when I do this by trial and error, this is actually an easy one, x plus 4, x minus 1. Okay, so nothing cancels with the top. This factor and this factor are not the same factors that we have on the top. So I'm going to rewrite this, and I'm going to say y equals 2x plus 3, and my factors are x plus 4 and x minus 1. Does this function have any holes? No, because nothing cancels. Okay, so now this says let's find the vertical asymptotes. Set each factor equal to 0 and solve for x. I'm going to change this. Set each factor in the denominator equal to 0. So what I have is x plus 4 equals 0. So I have a vertical asymptote at negative 4. And x minus 1 equals 0. So I have another vertical asymptote at x equals 1. So what I have here, if I was to graph this, and we're not going to go in and graph all of this, I would have one asymptote here, and I would have another one here. So now I'm going to have multiple vertical asymptotes, and it's all because the denominator doesn't cancel. All right, so without graphing, we're going to do this. So first thing that I have to do is I have to factor this. So when I factor this top, and if you are struggling with factoring, you've got to come see me, because this is like you can see it's not going away. So x plus 3, x minus 1 over x minus 1. So let me check it. I have negative 3. 3 minus 1 is positive 2. All right, so what do I see? I see that these two factors cancel. So this means I have a hole, and that hole is going to be at 1 something. I have to test this. I have nothing else in the denominator, so vertical asymptotes, none. All right, now, if you remember, what we did is we said a hole is a value. I can't just say there's a hole at 1. So I have to take it and plug it back in. So when I plug 1 back in for x, remember these are gone, when I plug it back in, I get 4. So my hole happens at 1, 4. All right, so now this one doesn't factor on the numerator, but it does in the denominator. So I end up with x plus 4, x minus 3. So negative 12, and then I have 4 minus 3, which is positive 1. All right, so holes. These don't cancel. These are different. X plus 3, x minus 3, they're different. So holes are going to be none. My vertical asymptotes happen when my denominator equals 0. So here I have 2 of them. So it's going to be at x equals negative 4 and x equals 3. I have 2 VAs on this problem. All right, here we go. This is most complicated. I have to factor both. So I have x minus 3, x plus 1. That gives me a negative 2. And down here, I'm going to have x minus 3 and x plus 2. So this is negative 6 and negative 1. Okay, so let's go here. We're going to check our holes, and we're going to check our VA. So here's the first thing I see. X minus 3s are going to cancel, so I'm going to have a hole at 3 something. I have to plug it in. So if I plug this in, I get 3 plus 1, so 4 in the numerator, and 3 plus 2, 5 in the denominator. Yes, it's a fraction, but that's the way it worked out. Vertical asymptote, what's left? This is left in the denominator now. So the VA happens at x equals negative 2. So you have a little bit of everything going on. Okay, now we're going to move on to something else. So what we did up here was vertical asymptotes, and what we're doing down here is horizontal asymptotes. So if you remember, when we went back and said we had some, hold on, let me get this out of here. We had some equation like this in chapter 7. We said we have a vertical asymptote at negative 3, so up and down. We have this horizontal asymptote at negative 3. So I have, if I was to graph this, at negative 2, I would have this guy, and at negative 3, I would have this one. Okay? So what we just did is we said, all right, we can identify where our vertical asymptotes are, but now we have to talk about the horizontal. We have to talk about the asymptote that is on the y direction. So I'm going to give you some notes here that are just standard vocabulary at Legacy, and then I'm going to talk about how I do this a little. I'm going to give you one of my stupid little phrases. So horizontal asymptote describes the end behavior. What happens out at the very end of my graph. So at infinity or negative infinity, what's going on? In other words, a horizontal asymptote shows where the y value approaches, where it levels off. And what we say here, what you're going to hear me say is approach. What does the value approach? Okay, so as the x values get large, so as we go to infinity, or as we go to the right, or as we go increasingly small. So as we go to negative infinity, so we're going in the negative direction, which is to the left. So what we're going to have when we create these asymptotes is you're going to create, or you're going to compare the degree of the numerator and the denominator. Okay? So in this is an example where the numerator is less than the denominator. So I might have something that looks like this. X plus 1 over x squared plus 1. So here, my denominator is, my power of my denominator is bigger than the power of my numerator. All right? So when this happens, we say y equals 0. What I am going to say is Bobo. Bigger on bottom 0. I'm going to write this out for you in a minute, so just stick with me and then we're going to write this out. Right? When the numerator is greater than the when the numerator is greater than the denominator. So that would be the opposite, x squared plus 1 over x plus 1. So I have a bigger degree in the numerator than I do in the denominator. Okay? And so this is no horizontal asymptote. And I'm going to say BO2. All right? And then we have a case where the numerator equals the denominator. So I have x plus 1 over x plus 1. These have the same power. And what we say here is y equals the coefficient on the top, the coefficient on the bottom. And I'm going to say bet C. Bet C. Okay? Now, keep in mind, a graph will never cross a vertical asymptote. Asymptote. But it can cross a horizontal asymptote. Okay, so now what I want you to do is grab a piece of paper, or you can write it on the bottom. There's not a lot of space here, but I'm going to go back to my Bobo, Betsy, Bo2. So I'm going to say this over and over and over in class. Bobo, Betsy, Bo2. So I have these two that I do backwards, right? So I'm going to write Bobo, Betsy, Bo2. And you'll see here in just a second how I'm going to apply these, but I'm going to just give this a setup so that you can go back and look at this. Sorry, here we go. And what I would tell you right now is write these on a note card or a sticky note or something where you can look at them a lot. So what this means is bigger on bottom. Bigger on bottom. When that happens, y equals 0. My asymptote happens at 0. So my asymptote is right here at 0. This one is bottom equals top. Bottom equals top, and what we say here is that this is going to be the coefficient. So if I had something that looked like this, y equals 3x squared plus 4 over 7x squared plus 5, I'm looking at the coefficients of my term. So I want the coefficient of this and the coefficient of this. So if I take and write this out, I would have 3x squared over 7x squared. My x squareds are going to go away. So here, my coefficient happens at y equals 3 over 7. So bottom equals top coefficient. The coefficient just means the number in front of the numerator, the number in front of the denominator, and I get 3 over 7. All right, and then my bow 2 is bigger on top. So Bobo, bigger on bottom. Betsy, bottom equals top. Bow 2, bigger on top. And when this happens, we get this U, and this U is undefined. So we say no HA. Now, my little cheat over here, my Bobo, Betsy, Bow 2, is the same thing that's here, right? This is mine. So you can just look at this. If you're like, that's corny, I don't want to do that, that's fine. You don't have to use this. You just have to know that if the numerator is smaller than the denominator, then your horizontal asymptote's always at 0. If the numerator is greater, there's no asymptote. And if they equal each other, then you just take the coefficient of the top and the coefficient of the bottom. So you either have to memorize these rules or stick with me when I say this over and over in class, Bobo, Betsy, Bow 2. Okay? And just refer to what that looks like. All right, let's practice. Let's look at this. So we are going to find our horizontal asymptote. All right, so find the horizontal asymptote if any of the following. So I have no x on the top and 1x on the bottom. So this is bigger on bottom. If it's bigger on bottom, it's a Bobo. Bigger on bottom, so y equals 0. So that's my horizontal asymptote. Here, I have an x and an x. So bottom equals top, Betsy. Bobo, Betsy, Bow 2. So my coefficient on the front is 1. Coefficient on the bottom is 3. This one is bigger on bottom. So this is a Bobo, bigger on bottom, y equals 0. Here I have 3x squared and x squared. So bottom equals top coefficient. So y equals 3 over 1. We never write it this way, so we would just say y equals 3. Now, it doesn't matter that I have another x here. This doesn't matter. I don't care. All I care about is my biggest power, my biggest degree. All right, here's another one. Bigger on bottom, Bobo, bigger on bottom. So y equals 0. Now, of course, this one is written a little funky, right? I have two factors. But if I was to FOIL these out, I would end up with an x squared on the top and an x on the bottom. So I have more on the top. So bigger on top is a Bow 2. And a Bow 2 means that there is no HA. So you can just say none or undefined. Okay, so again, I'm going to write this here. Bobo, bigger on bottom 0. Betsy, bottom equals top coefficient. And Bow 2, bigger on top, undefined. All right, and it's literally that quick. If you can remember these, then all you're doing is analyzing that first one. Okay, so now let's go back in here and look at discontinuities. And I'm going to add HAs in here because I think it's good practice. Okay, hold on, I'll be right back. All right, so we're going to put this all together. So if I want to find the discontinuities, the first thing that I have to do is factor it. So I end up with x plus 3, x minus 3, over x minus 3. Okay, so first thing that I have to do is see if anything cancels. It does cancel, so my whole is going to start at 3. And then I don't care about this anymore. I plug it back in, so 3 plus 3 is 6. So that's the second part of that term. Now I'm going to look here at if I have a vertical asymptote, this canceled out, so I have none. All right, so then the last thing I want to do is I want to look at my horizontal asymptote. So if I look at my horizontal asymptote, what I have here is bigger on top, undefined. So I have none. All right, so with this one, I have x plus 1. The bottom, I have to factor this because I can pull out a 3. So when I pull out a 3, I have x minus 2 in the bottom. Okay, nothing cancels. So I have no holes. All right. When my x equals 0 in the denominator, that happens at x equals 2. Now, I don't do anything with this 3. The 3 doesn't matter because there's no x there. Okay? So then the next thing I'm going to do is I'm going to look at my HA. So my HA are these two. And what I have is bottom equals top coefficient. They're both x's. So that's going to happen at y equals 1/3. Bobo, Betsy, Bo 2. All right. Over here, look what happens. This does not factor. This is not a difference of squares. This is not, I can't pull out a GCF. I can't do anything. So because I can't do anything, this doesn't factor. I'm not going to have any holes because nothing cancels out. And I'm not going to have any vertical asymptotes because I don't have anything in the denominator that's going to make this equal 0. So now I'm going to go in and look at my HA. And I have bigger on bottom, so that's a Bobo. So I do have an HA, and that's going to happen at y equals 0. You know what? I'm going to go ahead and pause the video, and I want you to do these last 3, D, E, F, and then come back on and check your answers. All right. Talk through this for just a second. You have to factor out an x on both of these. So hopefully you saw this. When you factor out just the x, that gives you a hole at 0. There's nothing else there, so what makes this 0 is 0. And then I take 0 and I plug it back in. So when I plug it back in, I get 5 in the numerator, and I get negative 2 in the denominator. All right, so this x minus 2 is left, so that's where my VA is. My VA is at x equals 2. And then I have x squared and x squared, so it's bottom equals top, coefficient, so y equals 3. Okay, this doesn't factor. I can't pull anything out. I cannot cancel these x's right here because I have this plus 1, so I have no holes. But remember, I do care where the denominator equals 0. And here the denominator equals 0 at 0, so I have a 0 here. It's different than this one because it doesn't matter what number I put in, I can never make the denominator equal 0 here because I always have this plus 6. If I put in a negative number and square it, it's positive. If I put in 0, it's still 6. So that's why I don't have a VA here. And then with this one, it's bigger on bottom. X cubed is bigger than x, so it's a Bobo, so y equals 0. All right, so this was in factored form. So if I multiply these two things together, I get an x squared. So I have x squared over x, so I have a Bo 2 bigger on top. So I have no horizontal asymptote. I see that these cancel. So if they cancel, I have nothing left in the denominator, so I have no vertical asymptote. And when I look at my factor here, this becomes negative 2, so my hole happens at negative 2. These are gone, so I plug it back into the original equation. So negative 2 minus 5 is negative 7. So my hole happens at negative 2, negative 7. Okay, I know there is a lot going on in this lesson, so we're going to practice this some more in class, but come see me if you're struggling.